Hi, everyone. I'm going to be recording some problems similar to the ones on midterm 3. And they're probably also relevant for the homeworks that are due this week. So let me log my tablet in, and we'll go ahead and get started. Okay, so I will get a whiteboard. And these are just some problems I thought up that are similar to ones you might see. So let's call this number 1. I want to find the equation of the secant line to graph y equals 10 to the x. Okay, so Daryl loves to give problems related to this function, and we're going to say that the secant line goes through the points. So we'll give 2 x values, say x equals 0.1 and x equals 0.5. So I am not going to be able to show the graph that Daryl has, so I encourage you to bring up the exam. It's right there on the second page. But just roughly sketching what we're thinking, this goes from 0 to 1. This goes from 0 to 10. This is 1. We have some graph like that for y equals 10 to the x. And we're hoping to find the equation of the tangent line, or sorry, the equation of the secant line that goes through these 2 points. Okay, so I'll draw the secant line in blue. Secant line is just the line connecting those 2 points on the graph. Okay, so just because I'm thinking ahead, it's probably going to be useful to get these y values. So let's just estimate what these y values are. For 0.1, I'm going to guess that, my y value is approximately, it's like just above 1.2, so I'll say 1.25. And then for x equals 0.5, that one almost exactly crosses at 3.2. Let's say it's 3.18, since it looks like it's a little below 3.2. Okay, so you can think about this. Maybe we'll call this y2. This is y1. This was then x2. This was x1. Those are just equal signs turned on their side. Okay, cool. So to find the equation of the line, then we should need 2 things, right? So let's work this out. Need 2 things. And actually, I can choose what things I need. I'll definitely need a point. And then I could either have the slope or an intercept. Or sorry, we could either have, slope and intercept or point slope, either one. We're going to go with point slope because we already have some points. It should be easy enough to find the slope of this line. So let's do that. Let's pick a point. Let's just pick the point, this first point. So that'll be 0.1, comma 1.25. Okay, so I'll use that later. We'll just hold on to that. And the thing that'll require a little bit more work is what is the slope? Okay. Slope is generally rise over run. Or I could write this out as y2 minus y1 over x2 minus x1, where y2 and y1, x2 and x1 are defined as shown on the graph. Okay, so that's then 3.18 minus 1.25 over 0.5 minus 0.1. Okay, and we can work that out. I think you're supposed to do all of this in your head, but because I'm not a student, I'm going to use a calculator. That comes out to 4.825. And to make Daryl think I didn't use a calculator, I'll just show 2 decimal places. Okay, so 4.82, that's going to be our slope. Maybe I'll call it M. Why not? Okay, so we have slope, we have a point. We should be able to use point slope form for the equation of a line. Okay, so let me remind you guys what that is. Point slope is, not sure if you guys generally write it this way. There are different ways to write it, but that's the way I think of it. Okay, and then we can just plug in. So I get y minus 1.25 equals the slope, 4.82, times x minus x1 was 0.1. That was that point. Okay, and then we can simplify that. I'm not gonna bother, but you guys have to, right? Because Daryl expects it to look something like y equals mx plus b. So I'll let you guys manage that. And we will go on to another problem. Next problem. Maybe I'll call this 2. I'm going to give this 3 parts. First, I'm going to define the function though. I'm going to say this is x cubed minus 3x squared minus 9x plus 1. Part A is going to be find the equation of the tangent line. This is my abbreviation for equation of tangent line. I have to tell you what tangent line, which x value is it located at. We're going to say x equals 0. Okay. Then we're going to have part B and part C. I'll just put them all together. Part B is going to be similar. Find the equation of the horizontal tangent line. Maybe lines. And for this, I'm not going to tell you what the x value is. You'll have to figure it out yourself. And then for part C, I want to ask, like, what is the x coordinate? X coord, where, let's say the second derivative equals k. Okay, so that's a weird question. And so let's get started. Let's work on A. Or actually, let's just compute some things first. So I'll do a little sidebar, a little note over here. We have y defined as such. So let me just write that down again. And then we'll compute all of the derivatives, well, up to the second derivative. So y prime and y double prime, because we'll need both of those. Y prime, remember to take the derivative of x cubed, I bring the 3 down and then decrease the exponent by 1. Okay, same story for the for this term. I bring the 2 down, multiplies the coefficient 3. So that's minus 6, x to the 1. X to the 1 is just x, so I'll just write minus 6x. And then similarly, 9x is like 9x to the 1. Bring the 1 down. Okay, 1 times 9 is still 9. And then I have x to the 0. So, I mean, that's a lot of work to go through. Most people think if you just have an x and you're taking the derivative, kill the x. And so that's minus 9. I'll write that in the red. And then derivative of a constant is 0, so I don't need to write that. Okay. that was too fast for you, that would be an indication you need to go back and review. This should come like clockwork. Some of the other derivatives will take more time, but you should be good with power rule when it comes to like nice whole number exponents. So practice that if you're struggling. And then we'll go ahead and take the second derivative. So the derivative of this expression, well, again, bring the 2 down. That's 2 times 3 is 6x. And then derivative of this term is just -6. Okay, so that's my second derivative. So I'll keep those handy, and then we'll go ahead and solve part A. So part A says find the equation of the tangent line at x equals 0. Well, to start, I could find the equation of the tangent line in general. And to think of that, well, a tangent line comes from a derivative, right? The derivative tells you the slope of the tangent line. Okay, so reminder, derivative is slope of tangent. So if I want the full equation of the tangent line, well, all I need is the slope and a point. Cool. So that should be helpful. Since that's true, let's go ahead and write down our derivative. Luckily, we already calculated it. So we have y prime equals 3x squared minus 6x minus 9. And in particular, I want to know what is y prime at x equals 0. Okay, right, that's the point I'm concerned with. So I'm trying to figure out the slope at that point. Okay, pictorially, you might be thinking, okay, I have some function. Here's the point on the graph at x equals 0. So this is like 0 comma some y value, I don't know. And I'm trying to find first the slope of this tangent line, but then also the full equation. Okay, so this gives me the slope in general. I want to know it at x equals 0. So I just plug in 0. Okay, so y prime at 0 is going to be 3 times 0 squared minus 6 times 0 minus 9. Okay, all these terms with 0 are just 0. So I just get minus 9 here. Okay, so that's my slope at the point I'm interested in. And so what is the equation? Well, the equation of the tangent line is just going to be, as usual, again, I can write this formula down. Okay. I know that this is -9. I know that x1, the point I'm concerned with, is x equals 0. I don't know what y1 is. So how do I figure out what y1 is? Well, if x1 equals 0, then y1 equals what I get just plugging my x value into that equation. So y equals 0 cubed minus 3 times 0 squared minus 9 times 0 plus 1. So that just equals 1. So you can go ahead and plug all that information. Right? We have y1, we have the slope, we have the x value. Plug all that in, get it in a nice form, and you should be good to go. I'm only half completing these solutions, but hopefully it's helpful nonetheless. I'm going to erase this, and we're going to go into part B. Part B is asking for the equation of the horizontal tangent lines. And yes, there might be more than one. So what we need to think about is, when is a tangent line horizontal? Okay, so we'll think to ourselves, tangent line is horizontal. Horizontal, just abbreviate, for example, like here, right? If I pick this x value and I drew a tangent line, it would be flat. Okay, it's a horizontal line. The defining characteristic of a horizontal line is the slope is 0, right? So tangent line horizontal when slope equals 0. Okay, and when I say slope, I'm really talking about derivative being 0. Okay, so again, we have our formula for the derivative. This implies we should just set it equal to 0. So y prime is 3x squared minus 6x minus 9. I want to set that equal to 0. And there are multiple ways to solve that equation. You could use the quadratic formula. That's a little tedious. What I would do is I would notice each of these as a factor of 3. 3, 6, and 9 are all multiples of 3. So I could pull a 3 out. That makes it a little more manageable. And then looking at the term or the expression in parentheses, I see I can actually factor that. So that might take a little bit of thinking, but I would definitely have an x minus 3. And I think the other term would be x plus 1. Okay, we can FOIL that out to double check. Those terms give me my x squared term. Negative 3x plus 1x is negative 2x. And then negative 3 times 1 is negative 3. So that's good. And then solving this, I can just set each piece equal to 0 separately. Okay, so that would give me x equals 3. This other piece would give me x equals negative 1. Negative 1. Okay. But that's not all, right? That's just the x value. Those are just the x values where the tangent line is horizontal. It's not the equation of the tangent line like we wanted. Okay, so for the full equation, we're going to need to know the y values. Right? Basically what I did here is, I'm going to erase some of it, but not all of it. Let's go back up to this drawing. Basically what I did was I found these two places. This graph isn't correct. Right? I'm just drawing some arbitrary cubic polynomial. But what we did was we found where these tangent lines were horizontal. And now we need their equations. And so like this was at some x value, this was at some other x value. And I want the equations of these green lines that I drew in. Okay, let me erase some of my work. Swipe space. We'll keep the x values down here because I need to remember those. Apologies for it flickering in and out, by the way. Okay, so when x equals 3, what is our y value? And when x equals negative 1, what is our y value? Right, I want to know what these red points actually are on the graph. Okay, I can figure that out by plugging into the original equation. So that would be 3 cubed minus 3 times 3 squared minus 9 times 3 plus 1. Whatever that works out to be, I think it's negative 26. Then if I plug 1 into, or negative 1 into this equation, I get something. Give me a second here. Is that right? 6, I think. I think I got 6. Not entirely positive. Hopefully that's correct. Okay, so those are the two red points on this graph that I was drawing. And that actually tells you everything you need to know. I'll let you think about that, why that's everything that you need to know. That you can write the equation of the tangent lines with just that information. Also, by the way, I think the problem on the midterm, you only have one tangent line. This one's a little harder than the one on the midterm. So if you understand this, you should be good to go. But yeah, it's simpler than, if it doesn't occur to you, it might be because it's simpler than it seems. But I've actually written the equation of the tangent line on here. So once you find it, you should be good to go. All right, let's try another problem here. Part C says, what is the x coordinate where the second derivative equals something that we're calling k? Okay, so k is just a number. I don't know what number it is, sadly, so I'll have to mess around with letters instead of just numbers, but that's okay. We're pretty good at algebra now. So what is the x coordinate when the second derivative equals k? That part of that sentence should imply I take the second derivative here and just set it equal to k. So y double prime was 6x minus 6. If I set that equal to k, and I want to know the x coordinate, that implies I should just solve for x. Solve for x. Well, my first step could be, erase some of these notes. My first step could be, I mean, I can pull a 6 out, right? Why not? And I would be left with x minus 1 in parentheses. That's equal to k. Divide by 6. And I get that. And then just adding 1 to both sides. So k over 6 plus 1. And yeah, that's the x coordinate where that happens. Just to see, maybe like, let's pick a value of k. What if k equaled 0? Would this make sense? Well, I'm asking where the, what is the x coordinate when the second derivative is 0? So I'm asking, when is 6x minus 6 equal to 0? Okay, again, could pull the 6 out and divide by 6. That's like saying, well, x equals 1. Okay, and if you were to graph this thing, well, I don't know if you guys know the graphical interpretation of the second derivative yet, but it would make sense. One thing I could note, actually, that's kind of interesting, which would maybe make you agree with me, is x equals 1 falls squarely in between the two x values I found in part B. We had x equals -1 and x equals 3. And my answer for part C that I have circled in red, x equals 1, is right in the middle of those two. Right? It's like 2 away from -1 and 2 away from 3. And that's because this is a nice cubic polynomial. It would actually be that point. And it's kind of this nice kind of symmetric thing. So it makes sense that it should be smack dab in the middle. Anyway, the problem on the midterm doesn't ask about the second derivative. It just asks where the slope is equal to k. So again, it's a little simpler than this one. I just wanted to give something that I thought was a little more interesting. Okay, so I'm going to clear this drawing and we'll try another problem, or another series of problems. Maybe I'll call this question 3. And again, we'll have a few parts. Let's say I wanted to take the derivative of some ghastly expression. Let's say it was this. Okay, that's kind of hideous, but let's give it a shot. Okay, the first thing I would do here is I would forget about this derivative and try to simplify algebraically. Okay, because honestly, you guys don't know how to take derivatives like this without simplifying first. So by simplify, I mean distribute this in to each of those terms. Okay, if I were to do that, well, 7 times 2x is 14x. So that's 14x over the square root of x. And the second term is 7 times 4 is 28. X times square root of x is, I'll just write x times square root of x. Okay, so that's the thing I want to take a derivative of. Keep my ddx out here. Okay, well, that's going to be the derivative of each piece individually. But before I do that, let's see if I can keep simplifying. So to simplify this first term, I need to know what is x over square root of x. And so let's come down here to a little sidebar. There are two ways to think about this. So I'll call this 1 and I'll call this 2, however you prefer to think of it. Some people might look at this and think that's x over x to the 1/2. Okay, and then by rules of exponents, this is like, well, x to the 1 over x to the 1/2, and I can subtract those exponents. So that's actually x to the 1/2. Okay, the other way to think about it, which I kind of like, is you can think about this numerator, x, as square root of x times itself. Right, square root of x times square root of x is x. And that doesn't really make sense if x is negative, because then you'd be taking a square root of a negative number, and that gets kind of weird. But okay, and then I'll keep the denominator the same, square root of x, and then you can think about just canceling a pair of those. And so that's just square root of x, which is x to the 1/2. So either way, that simplifies to x to the 1/2. Sorry, I'm scribbling really quickly. And we have this 14 out front. Okay, so that's 14x to the 1/2. Okay, and the second term, I definitely have that 28. And the way I would think about it is 1 over x squared of x, same as 1 over x times x to the 1/2. And again, you can use some rules of exponents. X times x to the 1/2 is the same as x to the 1 plus 1/2. So that's x to the 3/2. But whenever I have a power of x in the denominator, I can bring it up to the top. Okay, so I'm just going to put that up here. That's 28x to the negative 3/2. And that's the thing I want to take a derivative of. Okay, I'm going to erase my other stuff. Not the whole board, just sidebar. Okay, now taking the derivative here, we can just repeatedly apply power rule. So the derivative of the first piece, okay, bring that 1/2 down. And I get 1/2 times 14 is 7. And then I subtract 1 from the power. So the power is now negative 1/2. Similar story over here. I bring the negative 3/2 down. Okay, and I made these numbers uglier than I should have, but I think that ends up being 42. And then I subtract 1 from the power. So negative 3/2 minus 1 is negative 5/2. So that's how I would write that. I'm not sure if Daryl wants you to write it back in a form that was similar to the original, but if we wanted to, we could write it like this. I mean, that's x squared square root of x. Anyway, I think that form's probably fine. Cool. And let's look at another one. Let's say part B asks for the second derivative of this thing. Where a, b, and c are constants. So I'll make a note to myself. A, b, c are just constants. They're just numbers. Okay, well, if we want the second derivative, we should start by taking the first. So So let's do that. First derivative of this would be bring the 2 down, and I get 2ax to the 1, so 2ax. Derivative of bx is just b. Derivative of c is 0. Right? C is just a constant. So that's good. Then the second derivative would be the derivative of that. So I'll copy it in here, take the derivative. Derivative of 2ax is just 2a. Derivative of b, well, b is constant, so derivative of b is 0. Okay, so just 2a plus 0, just 2a. Cool. Let's do one other weird one. I'll call this 3c. What if I wanted the derivative of 2 over x to the k plus 3k to the 5th minus e to the negative 2k x. By the way, if it's not clear by this point, you should be pausing the video every time I write a problem and doing it yourself. Otherwise, you might get tricked into thinking you know how to do these things when really it just becomes apparent after you see how to do it. So don't fall into that trap. Okay, again, I would simplify this. So I would say that's the same as what? I guess there's not much simplification to do. The only thing I would notice is I have x in the denominator. I could bring it up to the numerator if I make the exponent negative. So that's 2x to the negative k. Okay, everything else is the same. And we're noting k is a constant. Okay. So we'll take the derivative of each piece separately. This thing is x to a power, well, 2 times x to a power, but the power rule still applies. So I would bring this exponent down. So that would now be negative 2k x to the what? Okay, I would have to decrement my exponent by 1, decrease it by 1. So it was previously negative k. Now it's negative k minus 1. Okay, I can just write it like that. That's fine. Let's focus on the next part now. What's the derivative here? Okay, don't fall into the trap of thinking, oh, I'll bring the exponent down, and that's 15k to the 4. Think about why that's incorrect. We're taking the derivative with respect to x. Power rule is only valid when you have x to a power, like we did in that first term. Here, this is k to a power. K is a constant. So the derivative of constant is just 0. Okay. If it helps, think about what if k was equal to 2? Then 3k to the 5th would be 96, I think. And the derivative of 96 is 0. So whatever k happens to be, it doesn't matter. It's a constant. Its derivative is 0. Great. So now let's think about this piece. This is an exponential, so I can get away with just bringing the coefficient in front of the x down and leaving everything else the same. Bring that down. So that would look like, okay, negative 2k. Well, these are both negative, so multiplying them would get me a positive 2k. And then I just copy the rest down. Okay, so that's my derivative. Obviously, I don't have to write the 0. And maybe I could simplify some things, but let you guys handle that. All right, and we'll go on to the final problem. So let's call this 4. And I think I'm just going to pull this problem from one of the practice midterms. What do we have? Fall 2016 looks reasonable. So this is something from fall 2016. Midterm 3. It says, after t seconds, I think this is pretty similar to one of the problems. Yeah. Because the last problem on the real midterm asks about Velocity, like throwing a coconut up in the air and talking about its velocity and stuff. So it should be fairly similar. So it says after t seconds, the height above the ground that's measured in meters of a rock falling vertically is given by some equation, h of t equals 728 minus 4t squared minus 30t. Okay. It lands on top of a building after 10 seconds. So instead of saying after 10 seconds, I'll say at t equals 10. Okay, part A asks, what was the velocity of the rock after t seconds? Well, velocity is the derivative of position. In this case, position is height. Okay, so the derivative of 728 minus 4t squared minus 30t, this thing. Well, derivative of 728 is 0. The second term would give me a negative 8t. The final term would give me a negative 30. So that's my velocity. Awesome, just take the derivative. Part B says acceleration of the rock after t seconds. Okay, well, acceleration is the derivative of velocity. Okay, so that's the derivative of a negative 8t minus 30, which is just negative 8. It's constant acceleration. Cool. Part C says, what was the initial speed of the rock? Okay. Also, thinking back to part A, I'm not sure if that should be 8t plus 30, because it depends on which way your y-axis is oriented, what up is and what down is. So you guys can think about that on your own time, but no worries. We'll just keep going. The initial speed of the rock, well, that's when t equals 0, right? So what is v of 0? Well, use the equation for velocity. Negative 8 times 0 minus 30 is just negative 30. I don't think he wants units here, but that would be in meters per second. Great. Part D, what velocity did the rock hit the building with? So maybe I'll erase part C and get part D down here in the mix. D. Well, we know the rock hit the building at time t equals 10. So just plug 10 in. I know you guys can do that. And then part B is maybe more interesting. How high is the building? Well, if we know that it hits the building at time t equal 10, then we should be able to get away with just plugging 10 into the height. Assuming everything was relative, the height function was relative to the ground, and I think it is. Right, this is height above ground is given by this. That means the top of the building is h of 10. And again, I'll let you guys, well, I guess I could do it quickly. That's minus 400, minus 300. I think that's 28 if you plug it in. So that's 728 minus 4, 10 squared minus 30 times 10. That's 728 minus 400 minus 300, which is 28 meters. All right, maybe I'll glance back, see if anything else stands out. I'm sure the CO2 problem is going to give you guys a headache, but don't want to give everything away. So yeah, I think that addresses most of the challenge. So hopefully you guys found this useful. I'm going to go ahead and clear this screen. And yeah, I wish you luck. So don't forget the midterm is due at, I think it's 10 a.m. on Wednesday. So I'm going to post this on Tuesday, and hopefully it helps. All right. Have a good week. See you guys in section.